Hey everyone, and welcome. If you're a researcher, you know that picking the right statistical tool can literally make or break your entire study. So today we are diving deep into a really powerful and flexible method called PLS SEM. We're going to break down exactly when and why this might just be the perfect tool for your work.
So, does this sound familiar? You've got this amazing, complex theory you've built, but you're kind of worried your sample size is too small, or maybe your data just isn't that perfect, clean, normal distribution. We've all been there. It is a classic research roadblock. But what if there was a tool that was practically designed for these exact situations?
And that, right there, is the researcher's dilemma. In statistical analysis, one size never, ever fits all. Choosing the right technique for your specific question, for your specific data, well, that's the absolute key to unlocking results that are not just meaningful, but reliable.
The world we're going to be exploring today is called structural equation modeling, or SEM for short. Honestly, you can think of it as this super-powered family of stats methods that lets us test these really intricate theories with a ton of variables all at once. It's the go-to when you're trying to map out complex relationships. Now, inside this big SEM family, there are really two main branches, kind of the two heavyweights in the ring. You've got covariance-based SEM, or CB SEM, and the star of our show today, partial least squares SEM, or PLS SEM. They both get the job done, but, and this is crucial, they have fundamentally different philosophies about how to do it.
So how in the world do you choose between them? Well, it all comes down to understanding what makes each one tick. We got to look past the nitty-gritty technical details and really focus on their core goals, what each method is fundamentally trying to achieve with your data.
Okay, this slide really gets to the heart of it all. It's like their DNA. CB SEM is what we call a confirmer. Its main goal is to see how perfectly your model fits the data you have. This makes it amazing for testing well-established theories. Think of it like a Formula One car. It's precision engineered for a perfect racetrack. On the other hand, PLS SEM is the predictor. Its main goal is totally different. It wants to maximize the variance explained in your key outcomes. It's built to predict. This makes it more like a rugged, all-terrain vehicle, designed to explore new territory and see what's just over the horizon.
Right, so with that foundation, let's get practical. Let's get down to the brass tacks. Here is a clear decision guide, basically a checklist you can use to figure out if PLS SEM is the right move for your project.
First things first, ask yourself this. Does your theoretical model look like a tangled web? Are there just a ton of variables, a ton of indicators, and all these arrows connecting everything all over the place?
If you answered yes, then PLS SEM has a massive advantage. See, with those super complex models, CB SEM can sometimes struggle to converge, which is a fancy way of saying it just fails to find a stable solution. It hits an error. But PLS SEM, it's built for that complexity. It is so robust, it will always produce a result, giving you a path forward when other methods might just hit a dead end.
Okay, next crucial question. What's the main point of your research? Are you trying to test a long-established theory down to the third decimal place? Or are you trying to predict an outcome? Are you trying to find the key things that drive a result you care about?
This is exactly where PLS SEM really shines. Its entire mathematical engine is built for prediction. Its goal is to maximize the explained variance in your outcomes. So if your core research question is all about what's going to happen next, well, PLS SEM was designed from the ground up for that exact job.
Now, because PLS SEM is so flexible, a few myths have popped up around how to use it. So let's take a minute and bust some of the most common ones so you can use this tool the right way and with confidence.
This is probably the number one thing you hear, right? Oh, you've only got a small sample? No problem, just use PLS. But is it really that simple? Can you just get away with a tiny sample size no matter what you're doing?
Yeah, the short answer is no. This quote really nails it. While it's true that PLS SEM can technically give you results with smaller samples than CB SEM can, that doesn't mean those results are any good. A sample that's too small is still too small, and it can lead to findings that just don't hold up in the real world, no matter which tool you use.
Okay, here's another one I hear all the time. A researcher looks at their data, sees it doesn't follow that perfect bell curve, and they immediately think, well, PLS SEM is my only option.
But that's not quite right either. While PLS SEM is awesome because it doesn't make any assumptions about your data's distribution, modern CB SEM actually has tools to handle non-normal data too.
So the takeaway here is that non-normal data doesn't automatically force you into one tool. It's a factor, for sure, but you still have to think about your overall research goals and your model's complexity.
Okay, so we've busted the myth that you can always use a tiny sample. But that leads us to maybe the most practical question of all. How big of a sample do you actually need? Let's see what the numbers tell us.
This is it. This is the million-dollar question for anyone designing a study, isn't it? You need enough statistical power to actually find the effects you're looking for, but you also don't want to waste time and money collecting more data than you need. It's a real balancing act.
This table gives us a really practical guide based on a power analysis. So just look at the columns for a second. If you're hunting for a small effect, you're going to need about 160 people. But if you're expecting a large effect, you might only need around 55. Now look at that first column. The number of arrows basically represents how complex your model is. And here's the crazy part. Notice how the sample size you need barely changes at all, even as the model gets way more complex? That is a fascinating insight.
So what's the bottom line here? It's this. The sample size you need depends way more on the strength of the relationship you're trying to find than on how complex your model is. If you're trying to detect some subtle, weak effect, you're just going to need a much larger sample to find it reliably. It's as simple as that.
So let's put it all together in a simple, 4-step decision flow you can use. Number 1, define your goal. Are you confirming or predicting? Number 2, assess your model. Is it simple or is it a complex web? 3, check your data context. And finally, number 4, and this is probably the most important one, plan your sample size based on the effect size you expect to find. And that kind of leaves us with one final thought to chew on. In a world where business and science are more and more focused on prediction, on what's going to happen next, should tools like PLS SEM, which are built for that exact purpose, start playing a much bigger role in our research toolkit? It's definitely something to think about. Thanks so much for joining me for this explainer.